Next, we'll be moving on to the second technical session. Over to Christy Benny for the welcome speech.
A very good afternoon to one and all gathered here. On behalf of our college, I welcome Dr. Jesty Thomas, who is an assistant professor in one of the most renowned colleges, K College Mananam, Kottayam. She doesn't require an introduction, as she is a well-recognized figure in the branch of chemistry. She was an associate board member of the international journal Nanoscience and Nanotechnology Asia, and also an editorial board member of the international journal Materials, Physics and Chemistry. She has also been a part of many international and national conferences. Her publications involve the never-ending knowledge about nanophysics, nanotechnology, and nanofibers. Her research projects include synthesis of phase pure anatase nanocrystals for the degradation of pollutants, synthesis of stable, highly luminescent inorganic organic hybrid materials by grafting lanthanide organic complex on nanozeolites, design and development of highly efficient semiconductor photocatalyst for the degradation of persistent organic pollutants under solar light, investigation on the synthesis of novel nanomaterials for the photocatalytic degradation of pollutants under sunlight. She has synthesized a new crystal structure which was accepted by Cambridge Crystallographic Data Center. She has been awarded the Outstanding Women in Chemistry and has also received the Best Research Paper Award 13 times. She has been recently awarded the Research Excellence Award 2020. I guarantee your next few hours will be delightful and memorable. Now, I welcome Dr. Jesty Thomas for chairing this technical session.
Thank you very much, Christy. Good afternoon, one and all. Now, the second session, technical session of this international conference is about to start. There are 6 paper presentations in this session, and all the papers are related to the topic of our international conference, nanomaterials, the recent developments and new directions. For the first technical session, first paper will be dealing with Ms. Shivangi, University School of Chemical Technology, Guru Gobind Singh Indraprastha University, New Delhi, and she will be handling the paper entitled "Is it some 5 catalysts for dehydration of glycerol to high value added products?" May I invite Ms. Shivangi to present her paper. Okay, then I invite Jagnan C. Upadhyay, Assistant Professor, Konkan Gyanpith Karjat College of ASC, Maharashtra. The paper is entitled as the study of surface morphology of metal notes by analytical methods and its application in water treatment.
And that I am doing on a mobile, and it is already in our full screen mode.
Yeah, it's okay, sir.
Okay, so myself is VSC, and actually my topic deals with the application in water treatment. Here, water treatment means we are collecting here water effluents that is contaminated with the synthetic dyes. So first, we'll discuss with what is the need of synthetic dyes. So synthetic dyes is having some positive aspects, like they are long lasting, means we can use, they have a washing proofness, and they have a wide range of choice, because the natural dyes have some selected shades. So the synthetic dyes can give a wide range of choices, and they have brilliant colors also, and they are also cheaper than our natural dyes, and definitely they have some easy process of dyeing, and reproducibility is there. Now, with these positive points, we have some negative aspects of the synthetic dyes. Now, what are the drawbacks of the synthetic dyes? They are often bio non-degradable, because of the chemical structures. There are aromatics and there are the structures in there. So they are non-biodegradables, and they pose health hazards, and they require skilled labors because these are the hazardous chemicals. So they require some skills in the hands of workers. And after releasing in the water resources, this causes water pollution. And my work also focus on the water pollution. Now, synthetic dyes are used by some industries that will name pulp, textile, pigments, paint, tanner. Now, here I focus on textile dyes, the dyes used by textile industries. Okay. Now, these dyes, when are released in the water resources, this poses some problems like they change the color of water and they decrease the access of sunlight by the aquatic plants, and they are already we discussed that they are bio-non-degradable, so they remain for longer time in the water beds, and they change the pH of the water, and definitely with these problems that change the taste and odor of the drinking water. Now, along with several methods like flocculation method, ozonation method, microbial degradation method, in our chemistry, we have one more method, adsorption method, that is widely used by the researchers. And because of ease of application, this is very easy process. Now, what are the benefits for the of this process is lower cost of the equipments because we need only adsorbent and some columns here, and ease of availability of the adsorbents. Now, process is efficient. This is proved by the earlier researchers, and process is very simple to apply. Now, the traditional steps which researchers have used in this process means purification of water contaminated dye using bioadsorbents. So first step, always the researchers have done that collection of water effluents contaminated with the certain dyes, and they select bioadsorbents. Now, why bioadsorbents? Because they are easily available, cheaply available, and they can be they are also recyclable. And after selection of bioabsorbent, they generally increase the surface area by activating the bioabsorbents. So this activation includes physical and chemical methods both. And then they characterize the bioabsorbent. Why characterization is needed? Because they want to see the surface area, whether this bioabsorbent is suitable for the adsorption process. And then after characterizing, they use batch absorption method to see the adsorption of the dyes on the surface of the adsorbent. And they study the thermodynamic properties and they study the kinetic models. Now, these are the certain steps used by the researchers. But what we have done here is we have discarded the last three steps and we followed the first four steps. I have to characterization bioabsorbent. Now we characterize our bioabsorbent. Then we have carried out our adsorption process, and then we were interested in changes brought about by the adsorption process. So this constitutes our introduction topic, that we characterize our bioabsorbent particles and we say that these are the very suitable adsorbents, and what happens to those properties after the adsorption process. So after adsorption, there are always superficial changes occurred on the surface of the bioabsorbent. Now, here bioabsorbent choose is betel nut husk, and here dye is blue red dye 22. So bioabsorbent choose is betel nut husk, and we prepared the bioabsorbent the following method that I will treat it briefly. That we have collected our sample and then we peeled out the fibrous part is collected, fibrous part is dried, and then it is chemically activated by using phosphoric acid. Then it was dried and in the oven at the temperature of 120 degrees Celsius. Then after drying, it was washed with 2% sodium carbonate solution. And after that, it was grinded and sieved to obtain the particle size of 250 BSS. And dye, we have prepared 1000 ppm of the dye as a stock solution. And for further dilution, we have used 20 ppm of the dye for the studies. So 25 ppm. And after obtaining the particle size of 250 BSS, we have put it to the activation variables whether these particles are suitable for the adsorption process. So we have found that ash content, water soluble matters, moisture contents, and pore volumes, bulk density, bed surface area, all this we have seen. I will discuss briefly. The water content is 2.1 and moisture content 2.8. It indicates that the compound is not hygroscopic in nature, and bed surface area was found to be 312 meters square per gram, which makes it suitable adsorbent for the studies. And these are standards. These all parameters or results obtained were as per the quality standards that mentioned by the SNI 1995. Then we have obtained SEM of the biosorbent particle, bitter nuts particle. This bitter nut has carbon was has shown this same properties, and the SEM was recorded before the adsorption and after the adsorption. So our aim was to see what happens to the porosity part. So SEM before adsorption has shown that bitter nut husk particles or adsorbent were having heterogeneous character and having large porosity. And then after adsorption of blue red dye 22 on the particles of bitter nut husk, we have seen that SEM has shown loss in heterogeneity. So loss in heterogeneity of the surface might have occurred due to the adsorption of blue red dye on the surface. And then we have recorded the FTIR also. FTIR before and after has shown some changes in the fingerprint region. We have there is no major change in the functional region of the IR, but in the FTIR after adsorption, we have noticed the azo functionality, that is azo group of the dye. So that is seen between the range of 1400 to 1450 per centimeter region. So this indicated that dye is successfully adsorbed on the surface of the biosorbent. So these are some changes seen in the FTIR of the adsorption process. Now we have recorded X-ray diffraction also. Now the X-ray diffraction, some differences are there. Some differences are noticed in the hanging peaks, and these hanging peaks were because of the adsorption process of the dye molecule, and these XRT have cleared that these particles are crystalline in nature, and we have noticed 2 theta of 20, 21, 23, and 26 at the respective positions. So we have recorded FTIR, same XRD, and same images. These 4 physical properties are studied, and what we have found is that we have mentioned the conclusion that PNHC, that is bitter nut husk carbon, after carbonization, it was found suitable for the adsorption process. So we can say that it is successful via adsorbent, and VNSC has effectively absorbed the particles of blue red dye 22, and there are some other parameters that we have mentioned in the steps that optimization are also required. So we can carry out batch absorption, batch methods of absorption, and for detailed idea that to study the nature of absorption between BNSC particles and blue red dye 22 particles, to see the nature and mechanism, we have to study that thermodynamic and quantitative data that will offer further attempt. Okay. Thanks a lot.
Thank you, Mr. Vinay Singh, for your presentation. Now the session is open for discussion. Audience or participants, please ask if you have any doubt. Can you reuse this adsorbent after adsorption?
Hello, madam. Pardon?
Have you studied the recycling capability of or capacity of this adsorbent?
No, madam. That was the part of batch adsorption method. That
Pardon
batch
me?
adsorption. That we have not studied the desorption method, because desorption parameter is included in the batch adsorption method. There we study effect of adsorbent dose, contact time, equilibrium time. All these parameters are studied in the batch absorption method.
Okay, then after once it is adsorbed, after desorption, can you reuse the same material?
If we see that there is successful desorption of the dye, then definitely, madam, we can use for the recycle purposes.
Okay. Participants, any question? Okay, thank you very much.
Thanks for that, madam. Thanks.
Participant delegates, kindly try to stick on your time. It's 10 minutes for your presentation. Now I would like to call Jisha George to present the paper entitled Morphological Variations of Some Nanocrystalline Metal Sulfides on Changing the Substituent at C4 position of a cyclohexanol-based thiosemi-carbazone sulfur sources.
Hello, madam. Hello.
Yeah.
Yes.
Yes. It is Atira MP to present catalytic performance of copper to supported mesoporous SBA 15 for Baeyer-Wilger oxidation of cyclohexanone to caprolactone.
Okay, ma'am.
Okay. Okay, Atira, ma'am, please start your presentation.
Yeah. Ma'am, can I start?
Yeah, sure. Please start.
Good afternoon to all. Myself, Atira, research scholar, Department of Applied Chemistry, Cochin University of Science and Technology. Today, I would like to present a paper, Catalytic Performance of Copper-2 Supported Mesoporous SBA15 for Baeyer-Williger Oxidation of Cyclohexanone to Caprolactone under the supervision of Dr. Suja Haridas, Assistant Professor, Department of Chemistry, QUISAT. Content of my presentation includes introduction, experimental section, resultant discussion, conclusion, and reference.
Can I continue?
Yes, sure.
Okay. Moving to the introduction part, Bayer-Vinegar oxidation reaction is one of the relevant reaction in organic synthesis for developing esters or lactones from respective carbonyl compounds. And oxidative conversion of cyclohexanone to caprolactone have tremendous application in polymer, perfume, and drug industries, and also widely used in degradable material, environmental protection, medical field due to its biocompatibility, non-toxicity features, and mainly three kind of oxidative system are used in Bayer-Vinegar oxidation reaction. The first one is organic parasites. Organic parasites are expensive, hazardous, and it limits their wide application in industry. And next one is hydrogen peroxide. It is cheap, safe, and green oxidant, and the problem is its poor stability and easy decomposition, which produce water, which hydrolyzes the product, and which have a low oxidizing capacity at its low concentration. And next, the oxidant that meet both environmental and cost concern is aldehyde and molecular oxygen. It is known as Makiyama method. Due to the speed up of initiation of radical chain reaction, molecular oxygen prefers different metallic or supported metal or metal oxide as catalyst, which show promising application in potential industry. Moving on to the catalytic part, use of support is identified as a handy tool to enhance the dispersion of catalytically active species, and supported metal oxide or mixed metal oxide and modified forms are suitable candidates to carry out the oxidation reaction with fairly good selectivity, and heterogeneous catalyst system play an important role in organic synthesis as it can reduce the number of steps and minimize the use of expensive harmful chemicals. And here supported copper catalysts have been used for this reaction. Among various silica based systems, SBA15, that is Santa Barbara amorphous, which have a good pore size in between 4 to 630 nanometer, and inert framework and thick pore walls, dual porosity, and high surface area, and which have studied as a well catalytic support since it developed. And this copper modified SBA15 is efficient catalyst for several reactions, including oxidation, cross coupling, hydrogenolysis, reduction of dyes, sensing, and etc. And next is the preparation of catalyst. Catalyst synthesis includes two steps. First one is synthesis of SBA, hydrochloric acid, pluronic 123, a block copolymer TEOS has mixed well, and it's placed in an autoclave for 48 hours. And the obtained material is filtered, washed, and dried and calcinated. And next step is the copper incorporation, which were done by wet impregnation method. And the prepared SB15 is treated with a copper precursor and calcinated at 550 degrees Celsius. And catalyst with different copper weight percentage were prepared by varying copper content, which is denoted as X copper SVA, and X may be 10, 20, 30, etc. And next is the Bayer-Vinegar oxidation of cyclohexanone to caprolactone, which were proceeded by employing benzaldehyde as a sacrificial oxidant under ambient atmospheric condition in acetonitrile as solvent using copper SB15 as catalyst, which is analyzed by GCMS technique using nitrobenzene as internal standard, and the conversion has been calculated by calibration method. Next, moving to the catalyst characterization section. This is the FTIR spectrum of SBA, 10 copper SBA, 20 copper SBA, which were given, and the presence of broad band in the low frequency region 3000 to 4000 centimeter inverse, centered at 3465, was characteristics of OH touching vibration of hydrogen bonded silanol group and a hydrogen bonded water molecule on bezo channels of silica, and the band occurs at 1080, 804, 484 centimeter is touching vibration bands of silicon oxygen silicon band, and band appeared at 960 centimeter inverse is resulted from silicon hydroxyl band, and copper oxide stretching vibration band at 536 centimeter is not that much prominent, and result demonstrated that significant amount of copper is successfully incorporated to the framework of SBA15. And the next one is XRD pattern, and low angle and wide angle XRD pattern. And in the low angle XRD pattern, pure SBA shows diffraction pattern at 0.96 degree, 1.67 degree, 1.93 degree to the plane of reflection corresponding to 100, 110, 200. And these are the characteristic peak of mesoporous SBA15. And retention of these peak in the modified sample indicates that parent structure is unaffected. However, there was no notable change in the D-spacing value for modified system. And next one is the wide angle XRD pattern, and the broad peak at 2 theta around 22.5 degree corresponding to amorphous silica, and all modified sample contain this peak, and intensity of this peak diminished due to metal content, and prepared system contains peak corresponding to copper oxide monoclinic structure, which attributed to the presence of copper oxide on the silica SBA15. And we have checked the necessity of catalyst in this liquid phase oxidation reaction. In the absence of catalyst, we didn't find any peak regarding caprolactone. In the presence of catalyst, we obtained a peak of caprolactone at retention time of 9.4545. And we have, and this is the percentage conversion of cyclohexanone in Baeyer-Villiger oxidation reaction. And table shows that it seems a similar conversion were obtained for 10 weight percentage and 20 weight percentage copper catalyst reaction. Around 17 and 80% conversion were obtained respectively, and the progress of the reaction was monitored using 20 copper SBA, and after 2 hours conversion was around 27%, and there is negligible conversion were obtained when reaction were done with SBA15. In short, copper SBA15 can act as a promising catalyst for cyclohexanone conversion to caprolactone, and this is the mass spectrum of cyclohexanone and caprolactone from GCMS. And in conclusion, copper incorporated SBA15 catalyst was successfully synthesized by a wet impregnation method, and catalytic activity of the prepared catalyst was examined for BV oxidation reaction of cyclohexanone to caprolactone, and comparable conversion were obtained for 20 copper SBA15 and 10 copper SBA15, and obtained a progressive increase in percentage conversion with time. This strategy, making use of green metal SBA15 as catalyst and employing air as oxidant under fissile condition, is a promising process which has high potential in industrial application. These are some references. Thank you.
Thank you very much for your nice presentation, Adira.
Okay, ma'am.
Now the session is open for discussion. Participants, kindly ask your doubts. Okay, I would like to ask you some doubts, or just for clarification. Have you studied the mechanism of this Baeyer-Villiger? You are not using MC peracids, hydrogen peroxide, etc. Then, what will be the mechanism of this conversion or this Baeyer-Villiger oxidation?
I have not included that in this slide. We are not using any hydrogen peroxide like oxidant. We are using benzaldehyde, and which initiated by radical chain reaction, and that kind of radical mechanism is here.
Have you studied that mechanism?
Yeah.
Okay. Then can you take the low angle XRD?
Yeah.
That slide. Okay, here in this low angle XRD, there is a slight shift in the peak at 10 CUSBA. That is that second sample.
Yeah.
Why that shift has come in that 1 theta angle?
2 theta angle.
Yeah.
That is due to the copper incorporation, ma'am.
But it is not there in 20, the blue one.
The first one is pure Sd15. The other
Yeah.
is blue is 10 copper, and the third one is 20 copper Sda.
Yeah, in the 20 copper, the peak is not much shifted, but in the case of 10, it is shifted. And also, it's not in the order. Can you explain why? Just for curiosity, I'm asking.
Yeah, I think I need to read on this.
Okay, and also in the just for I just want to convey you that is your experimental part. I think can you take your 6th slide? 6. Sorry, it's not 6. I think. Yeah, that's right. Here it is. You have written cyclohexanol. Please change it. It's cyclohexanol. Just for your information only. Okay, thank you very much.
Okay, ma'am.
Okay.
Good afternoon all. I am Jisha George, research scholar from Department of Chemistry, University College, Trivandrum. I am doing my research work under the guidance of Dr. K. Rajesh, Associate Professor, Department of Chemistry. The topic of my presentation is morphologic variations of nanocrystalline metal sulfides on changing the substrate that is seen for position of a cyclohexanone-based thiazomicarbazone sulfur source. Then contents. First one, introduction. Second, materials and methods in that synthesis of the ligands for medial cyclohexanone thiazomicarbazone and for tertiary butyl cyclohexanone thiazomicarbazone. Synthesis of metal complexes of the ligands. Synthesis of nanometal sulfides are included. Then results and discussion in that IR of the ligands and the metal complexes, proton NMR of the ligands, electronionization mass spectrum of the ligands, semidax of the metal sulfides from for medial cyclohexanone thiazomicarbazone, semidax of metal sulfides from for tertiary butyl cyclohexanone thiazomicarbazone, same images of synthesized nanometal sulfides, same images of synthesized nanometal sulfides are included. Then summary and conclusions, then reference and acknowledgements. Then first one, introduction. Thiazomicarbazons are important class of NS donor ligands because of interesting chemical, biological and medicinal properties. They are formed by the condensation reaction between an aldehyde or ketone with the thiazomic carbazide. They form complexes with the transition and non-transition metals with different densities. Their complexes can be used as single-source molecular precursors in nanosynthesis. And materials and methods. First one, for the ligand for methyl cyclohexanone thiazomic carbazone. For that, equimolar methanolic solutions of 4-methyl cyclohexanone and thiazomic carbazide along with the 10 drops of glacial acetic acid are refluxed for 3 hours and then cooled slowly. The thiazomic carbazone 4-methyl cyclohexanone thiazomic carbazone gets precipitated. Then for the second ligand for tertiary butyl cyclohexanone thiazomic carbazone, for that 4-methyl for tertiary butyl cyclohexanone and thiazomic carbazide are taken as equimolar methanolic solutions and they are refluxed on a water bath for 3 hours along with 10 drops of glacial acetic acid and then cooled slowly. The corresponding compound for tertiary butyl cyclohexanone thiazomic carbazone gets precipitated. Then synthesis of metal complexes of the ligands. For that, methanolic solutions of the ligand and methyl acetates are taken in 2:1 ratio as methanolic solutions. The corresponding metal complexes gets precipitated. The ligands are the previously synthesized for methyl cyclohexanone thiazomic carbazone and for tertiary butyl cyclohexanone thiazomic carbazones. And the metal salts taken are the acetate salts of zinc, cadmium, and mercury. Then the procedure used is for zinc and cadmium complexes. The reaction mixture is refluxed for 3 hours on a water bath and then cooled slowly. Then for mercury complex, only continuous stirring for 50 minutes is required for the precipitation of the mercury complex. Then these metal complexes are used as single source precursors in nanosynthesis. Then synthesis of nanometal sulfides. For that, the above prepared metal complexes are taken and they are subjected to thermal decomposition process in high boiling solvent glycerol at its boiling point, and the corresponding nanometal sulfides gets precipitated. Then IR results and discussion. First, an IR data of the ligands and the metal complexes. The band in the region 3200 to 3400 correspond to NH2 symmetric and asymmetric vibrations, and the bands within the region 3100 to 3200 correspond to NH vibrations, and the C double bond in bond gives vibrations within the range 1580 to 1620, and NN vibrations are in the range 1070 to 1100, and the C double bond S vibrations are around 850. In the case of complexes, MS vibrations occurs in 480 to 500 cm raised to -1, and the MN vibrations occurs at 500 to 580 cm raised to -1. Then proton and number of the ligands. First one, 4-methyl cyclohexanone thiazide carbazone. In that NH proton gives peak at 10.153, and NH2 proton gives two singlet peaks, one at 7.919 ppm and 7.492 ppm. This indicates that the two hydrogen atoms or two hydrogens of the amino group are not present in a chemically equivalent environment. The CH3 group present at the fourth position of the cyclohexanone ring appears at 0.65 ppm, and the remaining peaks correspond to the different hydrogen atoms present at the cyclohexanone ring system. In the case of tertiary butyl cyclohexanone thiazide carbazone system, the NH peak appears at 8.585 ppm, and the NH2 gives two peaks. The first one is a doublet that occurs at 7.263 and 7.223 ppm, and the second one is a singlet that occurs at 6.168 ppm. And then the fourth tertiary butyl group gives peak at peak of a high intensity peak, a sharp that occurs at a sharp singlet, and that occurs at 0.886 ppm. Then electronionization mass spectrum of the ligands. First one, for 4-methyl cyclohexanone thiazide carbazone, the peak appears at the first peak that appears at 186 AMU, that corresponds to M plus H peak. The molecular mass of the compound is 185 AMU, and the second peak that is formed by the loss of NH2 fragment, that gives a peak at 169 AMU, and the third peak that is formed at 110 AMU, that corresponds to the loss of correspond to the fragment that is formed by the loss of NHCS NH2 fragment. Then for the mass spectrum for tertiary butyl cyclohexanone thiazide carbazone, the first peak appears at 250 AMU, that corresponds to M plus Na peak, and the second peak is at 228 AMU, that corresponds to M plus H peak, and the molecular mass of the compound is expected to be 227 AMU, and the next peak appears at 211, that is formed by the loss of NH2 fragment from the molecule, and the last peak is formed at 152, that is formed by the loss of NHCS NH2 fragment. The next one is the same redox of the metal sulfides from 4-methyl cyclohexanone thiazide carbazone. In the case of zinc sulfide, the ratio between zinc and sulfide that is almost close to the nominal ratio between the metal and the sulfur. In the case of cadmium sulfide also, that is almost the same to the nominal ratio between the metal and the sulfur content. And in the case of mercury sulfide, there is a metal deficiency defect is seen in the crystal lattice. In the case of semidax of the metal sulfides from tertiary butyl cyclohexanone thiazide carbazone, in the crystal structure there is a large amount of O is seen. O is seen. That is because of the presence of a large amount of caping agent that is present in the crystal structure. And the ratio of sulfur is also very low compared to zinc. There is a deficiency in sulfur in the crystal structure is occurred. In the case of cadmium sulfide, there is the nominal ratio between cadmium and sulfur is almost maintained in the crystal structure. In the case of mercury sulfide, here also there is a metal deficiency defect is seen. In the case of SEM picture, from the SEM pictures of all these metal sulfides formed, it is clear that most of the particles are homogeneous in nature. Then better distribution of the particles are also seen, and it shows clearly an increase in surface area at nanometer regime. The crystalline nature of the particles are also clearly seen from the pictures. Then 10 images of the metal sulfides formed. These two are the zinc sulfides, represent zinc sulfides. And in the case of zinc sulfide formed from 4-methyl cyclohexanone thiazide carbazone, the particle size is from 3.15 nanometer to 5.93 nanometer. But when zinc sulfide is produced from 4 tertiary butyl cyclohexanone thiazide carbazone, the particle size is from 17.28 to 49.01 nanometer. In the case of the particle size is smaller when 4-methyl cyclohexanone thiazamic carbazone is used. In the case of cadmium sulfide, when 4-methyl cyclohexanone thiazamic carbazone is used, the particle size is from 5 nanometer to 8.83 nanometer. When 4-tertiary butyl cyclohexanone thiazamic carbazone is used as the ligand, the particle size is from 5.55 nanometer to 8.14 nanometer. The particle size is almost the same in both routes. In the case of mercury sulfide, the particle size when 4-methyl cyclohexanone thiazamic carbazone is used, the particle size is 34.7 to 96.84 nanometer. When 4-tertiary butyl cyclohexanone thiazamic carbazone is used, the particle size is from 14.63 to 24.82 nanometer. It is clear that when 4-methyl cyclohexanone thiazamic carbazone is used, the particle size is greater. Then summary and conclusions. The two ligands and their precursor metal complexes are prepared successfully in good yield at normal laboratory conditions. The corresponding metal sulfide nanoparticles are successfully synthesized using both the ligands for methyl cyclohexanone thiazamic carbazone and for tertiary butyl cyclohexanone thiazamic carbazone. For zinc sulfide, zinc is to sulfur ratio is 1:1 on using 4-methyl cyclohexanone thiazamic carbazone, and also the particle size is lower than the other ligand route. For cadmium sulfide, the amount of cadmium and sulfur were close to the nominal values in both routes, and the particle size are also the same. For mercury sulfide, there is comparable metal deficiency defect in both the routes, but particle size is smaller when for tertiary butyl cyclohexanone thiazamic carbazone is used as ligand. There is no much morphologic variations on changing the substrate receiver position of cyclohexanone thiazamic carbazone. Only one difference seen is in the presence of high amount of caping agent in the lattice of zinc sulfide when methyl group is replaced by tertiary butyl group at the C4 position. Then these are the references and acknowledgements. I extend my gratitude to Dr. K. Rajesh, Research Guide, Department of Chemistry, University College, Trivandrum. I gratefully acknowledge the financial support provided by the University of Kerala in the form of research fellowship. I thank the authorities of STIC, COSAT and NIST Trivandrum for providing instrumental facilities. Thank you.
Thank you, Jisha. Now the session is open for discussion. Participants, please clear your doubts, if any. Thank you, Jisha.
Thank you, ma'am.
Sister, I think all the presentations are over.
Yeah, yes, nobody else is here. I think 2 or 3 didn't come.
Pardon me, it's not audible for me.
Yes, I think it is over.
Okay.
2-3
Okay.
didn't
Then
come.
I think we can conclude the session, technical session 2.
Okay.
And first of all, I thank the delegates who have presented their papers to this session. And also, personally, I would like to thank the principal of BK College and Sister Raji for inviting me to chair this session.